The universe is an unfathomably vast expanse that stretches beyond the limits of our imagination. It encompasses everything from the tiniest particles to the largest galaxies, forming an intricate tapestry of matter, energy, and cosmic phenomena. Our adventure through this colossal realm begins with a simple yet profound question. How did it all begin? As we gaze into the night sky, we are reminded of the sheer scale and complexity of the universe. The countless stars scattered across the celestial sphere are but a fraction of the countless galaxies that populate the cosmos. Each of these galaxies is a collection of billions of stars, each with its own system of planets and moons. The universe in its entirety. The universe in its entirety is a vast network of interconnected systems governed by fundamental forces that shape its evolution over billions of years. The journey to understand the universe's origin and evolution is not just a scientific endeavor. It is a quest that touches upon our deepest philosophical questions. What is the nature of reality? How did life arise in this cosmic expanse? Are we alone in the universe? In this essay, we embark on a journey through time and space, exploring the origin and evolution of the universe. The Big Bang Theory offers the most widely accepted explanation for the universe's origin, proposing that it began as an infinitely hot and dense singularity. Approximately 13.8 billion years ago, this singularity underwent a dramatic and explosive expansion, setting the stage for the universe's continued evolution. In the moments following the Big Bang, the universe experienced an era of rapid expansion known as cosmic inflation. During this phase, the universe expanded exponentially, growing from a minuscule point to a size larger than the observable universe today in a fraction of a second. Cosmic inflation smoothed out the initial irregularities, laying the groundwork for the formation of galaxies, stars, and planets. The concept of cosmic inflation helps to address several perplexing issues in cosmology, such as the horizon problem and the flatness problem. Inflation explains this by suggesting that these regions were once close together before being rapidly pulled apart. The Big Bang Theory, with cosmic inflation as a key component, provides a coherent framework for understanding the universe's early moments. As the universe continued to expand and cool after the initial inflationary period, fundamental particles began to emerge. Within the first few microseconds, quarks and leptons, the building blocks of matter, came into existence. These particles interacted under the influence of fundamental forces, eventually forming protons and neutrons. This process set the stage for the formation of light elements, a critical phase in the universe's evolution known as nucleosynthesis. During the first few minutes following the Big Bang, temperatures were high enough for nuclear reactions to occur. Protons and neutrons combined to form the nuclei of light elements such as hydrogen, helium, and lithium. This period, known as Big Bang nucleosynthesis, was responsible for producing the primordial abundance of these light elements that we observe in the universe today. The cooling universe allowed electrons to combine with these nuclei, forming neutral atoms. This epoch, known as recombination, marked a significant milestone as it resulted in the universe becoming transparent to light. The formation of atoms set the stage for the gravitational collapse of matter, leading to the creation of stars, galaxies, and other cosmic structures. The Big Bang Theory is reinforced by key observational evidence. The cosmic microwave background radiation, CMB, is a significant piece of evidence. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB provides a snapshot of the early universe. Its uniformity and spectrum align with Big Bang predictions. Temperature variations in the CMB reveal early matter distribution. Another key evidence is the red shift of light from distant galaxies observed by Edwin Hubble. The red shift indicates an expanding universe. The further a galaxy, the faster it moves away, known as Hubble's law. These evidences support the Big Bang as the leading explanation for the universe's origin. Section 5. Alternative theories of the universe. While the Big Bang Theory is the leading model, several alternative theories exist. The Steady State theory suggests the universe has no beginning or end, with new matter continuously created. This theory lost favor due to evidence supporting the Big Bang, like the cosmic microwave background radiation. The multiverse theory posits multiple universes, each with its own physical laws. These theories show the diverse approaches to understanding the cosmos. Despite these alternatives, the Big Bang theory remains the most comprehensive model. Section 6. The universe's ongoing expansion. The universe's expansion is not a relic of its ancient past, but an ongoing process that continues to shape the cosmos. Observations indicate that not only is the universe expanding, but the rate of expansion is accelerating, driven by a mysterious force known as dark energy. This enigmatic component, which constitutes roughly 68% of the universe's total energy density, is responsible for the accelerated expansion observed in distant galaxies. Dark energy's nature remains one of the most significant puzzles in modern cosmology. Its discovery in the late 1990s revolutionized our understanding of the universe, suggesting that the future of the cosmos may be vastly different from what was previously envisioned. The concept of an accelerating universe challenges our conventional understanding of cosmic evolution. The study of dark energy and the expansion of the universe is a vibrant area of research, with scientists employing a range of observational techniques and theoretical models to unravel its mysteries. Section 7. Future Scenarios of the Universe. Contemplating the future of the universe invites a range of speculative scenarios, each based on our current understanding of cosmic expansion and dark energy. One possibility is the Big Freeze, where the universe continues to expand indefinitely, resulting in a cold and barren cosmos. In this scenario, stars will eventually exhaust their nuclear fuel, galaxies will drift apart, and the universe will become a dark and empty expanse. Another potential fate is the Big Crunch, a scenario where the expansion of the universe eventually halts and reverses, leading to a collapse back into a hot, dense state. This outcome would effectively result in a cyclical universe, where each big crunch is followed by a new Big Bang, giving rise to a fresh cosmic cycle. However, current observations of accelerating expansion suggest that this scenario is less likely. The Big Rip offers a more dramatic vision of the universe's end, where the repulsive force of dark energy continues to intensify, eventually tearing apart galaxies, stars, and even atomic structures. These future scenarios underscore the uncertainty and complexity of the universe's evolution. Section 8. Continuous Discoveries in Cosmology. The field of cosmology is a vibrant and ever-evolving discipline, driven by a continuous stream of discoveries and advancements. From the detection of gravitational waves to the mapping of cosmic microwave background radiation, each breakthrough brings us closer to unraveling the universe's mysteries. The advent of powerful telescopes and observational tools has revolutionized our ability to explore the universe. Instruments like the James Webb Space Telescope and the Large Hadron Collider are pushing the boundaries of what we can observe and understand, providing unprecedented insights into the nature of dark matter, dark energy, and the fundamental forces that govern the universe. These technological advancements are enabling scientists to test theories and explore phenomena that were once beyond the reach of human observation. At the heart of cosmological research is a spirit of collaboration and innovation. Scientists from around the world are working together to tackle some of the most profound questions in physics and astronomy. As we stand on the cusp of new discoveries, the future of cosmology holds immense promise. Section 9. A Thought-Provoking Conclusion. In exploring the origin and evolution of the universe, we journey through time and space, uncovering the secrets of the cosmos and our place within it. The Big Bang theory, supported by compelling evidence such as the cosmic microwave background radiation and the redshift of distant galaxies, provides a robust framework for understanding the universe's beginnings. While the Big Bang remains the leading model, alternative theories like the Steady State, Multiverse, and Plasma Universe theories offer intriguing possibilities, challenging us to expand our perspective and consider the vastness of potential realities. As we look to the future, the universe's expansion and the enigmatic force of dark energy pose profound questions about the cosmos's destiny. Scenarios like the Big Freeze, Big Crunch, and Big Rip invite speculation and wonder, reminding us of the complexity and unpredictability of cosmic evolution. In this cosmic journey, we are reminded of the importance of curiosity, exploration, and discovery. The universe is a boundless frontier, filled with wonders yet to be uncovered. Let us embrace this journey with open minds and hearts, inspired by the profound beauty and complexity of the cosmos that surrounds us.